So in today's class, we are going to talk about the design or modeling of the propulsion system. And this is an important component of quadcopter design, because when I started working about 10-15 years ago, it was very difficult to spec the quadcopter. The design process was iterative and it used to take a lot of time. Again, the design equations are the same, but now with the advent of software, there is a cloud-based tool that you can use to spec out and design the quadcopters very quickly. And also, you can actually sort of confirm your theoretical calculations with experimental results. And usually, I tried this tool and I tried some design options, and I found out that the designs that I could make, or actually I could look at the specs, they were fairly good. It was quite accurate. So the most important thing is we want our quadcopter or multi-rotor to fly. And there are 2-3 things when we say flying. First, we want it to hover stably. What do I mean by stable hover? Stable hover means the thrust generated from each of these props should cancel out, the total thrust should cancel out the weight. And you would see that even this seems like a very plastic frame. It's not light, it's quite heavy. So just for the quadcopter to hover stably is going to consume a lot of energy. So what is going to supply that power? So we are going to have a battery. So we need to understand what are the specifications of the battery that we need. There will be a motor, and this is the brushless DC motor. So as you can see, there are 3 wires, and basically this is the ESC, which acts like an electronic commutator, and basically it commutes and makes this motor rotate. You would also notice that every motor has something called as the kV rating. kV stands for, it's a factor that relates voltage to RPM. So for an example, this motor has 1000 kV, which means if I were to supply 1 volt to it, it will rotate at 1000 RPM. Usually the quadcopters are powered with 12, 24, 36 volts. So you will notice that this motor is going to rotate at very, very high speed. Another important concept that we need to take into account is the thrust that is generated by the prop is proportional, approximately proportional to speed. I will give you an expression. I'll talk about the expression. It also depends upon the diameter. It also depends upon the chord length. But in general, for a particular prop, if once you decided what are the dimensions of the prop, you would notice that the thrust generated by prop is proportional to the square of the speed. So speed is something that we will control using the ESCs. Now, one thing I want you to observe that these motors, they just have 3 wires coming in. Even though we are supplying positive and negative, basically what it does, it takes this DC current, DC supply, and converts that into an AC supply, 3-phase AC supply. And these phases, they run at certain phase angles that will cause this motor to rotate. This motor does not have sensors. There are some motors, they have sensors, and we need sensors or Hall effect sensors to understand the direction in which the motor is rotating. And so if you have ESCs that are a little bit expensive, more sophisticated, then usually they can run the censored DC motors and sensorless DC motors. Typically, brushless DC motors are used for quadcopters or multicopters, which are in this larger size. If you are working with Mambo or Telo, the motors that you have are permanent magnet brushed DC motors. That's why you see only 2 wires coming in. They are very good for low speed or low sort of power applications. And let's talk about the outline for today's talk. In today's discussion, we are going to talk about how do we model a propulsion system. And when I say propulsion system, it's the motor, it's the prop, it's the ESC, and the battery. So these are the 4 important components of propulsion system. Then how do we evaluate the performance of that propulsion system? And then we need to make sure that the propulsion system is capable in all the flight modes. Believe it or not, the quadcopter or the multicopter would have different flight modes. There could be a simple hover, it could be pitching, it could be rolling, it could be yawing, it could be maximum speed, or it could be maximum thrust. So your propulsion system should be able to support all these operation modes. And what I'm going to do is, I'm going to take 4 cases wherein typically what you do is, first and foremost, you design the UAV for a stable hover. Then you check the system that you have is capable for providing maximum thrust. Then if you have some additional requirements, like you want that UAV to loiter for certain duration of time, say operation time is like 20 minutes. You make sure that the system that you have selected is capable of supporting that much amount of power. And you actually go through these different test cases and finally come up with a final design. So, and then at the end, there is a website, or this is a cloud-based tool, which you can use to design a complete UAV. So if you are into building quads, and then you say that these are my design specs, and then what I want to do is I want to select a frame, then I want to select a motor, I want to select a ESC, I want to select a battery. You can supply all those requirements, and then the equations that we are going to talk about, those equations are programmed, and that actually would give you a configuration. And then you can perform some design of experiment, like what if type of analysis on that configuration. So this tool is web-based. In next class, I'm going to show you a MATLAB-based tool wherein the same equations are implemented in MATLAB, but it does not have a huge database. Here, since it's cloud-based, it has access to the database from different manufacturers of motors, different manufacturers of prop. So we will talk about the MATLAB-based tool in next class. Today we will look at the cloud-based tool. So we are going to talk about in today's class, what are the governing design equations for these 4 important components. How do you select or design a propeller? How do you select or design a motor? How do you select ESCs? And finally, how do you actually select a battery? And I know some of you might be familiar with the terms that are mentioned here, but just for my own satisfaction, I'm gonna quickly go to the terminology that is used when you are actually designing an airframe. So first thing is, if you have a prop, there is a diameter of the prop, and there is something called as the pitch of the prop, and there is something called as the chord length. So this is the prop. Now, when you look at the prop, I want you to understand, as this prop is rotating in the air, The shape of the prop is like an airfoil. The airfoil is slicing through the air. So when we are going to study the prop dynamics, we are going to take into account something called as the blade element theory. Like if you take a small strip of this prop, this becomes like a blade. And as this blade is swinging through the air, it's like slicing the air. The prop would have a leading edge and it will have a trailing edge. So leading edge is basically the edge that actually is going to slice. You would realize the trailing edge would be sort of, it won't be sharp, so it will be dull. So you can actually run your hand thumb like this. But the leading edge, this would be like super sharp, because what we want to happen is we want that airflow to separate and stick to the outer and inner surface, the top and the bottom surface. You do not want flow to separate. Flow separation is dangerous. Flow separation is bad. That's why you are going to have the leading edge that is super sharp, and then you will have this the trailing edge would be dull. Then you are going to have the blade number, which is nothing but the number of blades. We will also have the prop weight, or the weight of the prop. There are different types of props. There are plastic props like this. So basically they break quickly. The carbon fiber props, they don't break, but they will cut your fingers very easily. So be very careful when you play with carbon fiber props. Typically, whenever you see a prop, there will be something called as the thrust coefficient, Ct, and there will be a moment coefficient, Cm. Now, the airfoil concept is very simple. If you think about your palm, you just actually place your palm in the incoming flow of air. You would observe if you change the angle of attack, your palm and your hand would experience some drag and some lift, The CT component is associated with the lift, and Cm component is associated with the drag. What is the difference between a fixed wing aircraft and a rotary wing multicopter? In the fixed wing aircraft, what you have is, you would notice that you change the angle of attack and you can get different value of lift and drag. At certain point, at certain angle of attack, the aircraft would stall. Why would a fixed wing aircraft stall? Because at that time, the airflow would separate from the airfoil. And when there is a separation, that airflow is useless. It will not generate lift. Basically, that is the reason why that aircraft, when they are taking off, they need to have some speed so that the incoming air has enough velocity to generate, basically incoming air gives rise to dynamic pressure. Dynamic pressure multiplied by coefficient of lift would give you the lift on the airplane. So this needs some velocity. Aircraft will stall. It cannot go forward. It will not generate lift at certain angle of attack or at certain speed limit. So if the speed is very low, then the aircraft cannot fly. It's not the case in the case of quadcopters. So aircraft cannot fly in one place. Quadcopters can. For the motors, you would have something called as kV value, and for motor design, you are going to use the same principles of circuit design. You would use an inductor, and you would use sort of a resistance, capacitance type of network. It will also have some current requirement, current specs. The motor will also have a no load current, which is the current that is supplied, or the current that motor is consuming at no load. It will also have the no load voltage. Motor will have its own internal resistance, and it will have some weight. ESC is basically the electronic circuit board, and the way the electronic circuit board works is it will have MOSFETs, and then you actually, so they are like switches. you turn on and off them very rapidly so that you excite each winding in certain sequence that would make this motor, the brushless DC motor, rotate. But as far as we are concerned, we are going to model the ESCs with some sort of resistance, capacitance, inductance type of network. And at the end, we are going to have battery. The battery would have certain discharge rate, which is called C rating. It will also have some weight. It will also have total voltage, and it will have the total capacity. So the amount of energy that is stored, in the battery.
So for single rotary aircrafts, they encounter vortex wing states, quadcopters deal with that?
Yeah, the vortex. Okay, so I have. So what is vortex ring state? Now, basically, if you have a helicopter, the way the helicopter works is if the helicopter is trying to go down very quickly, if the helicopter is trying to go down very quickly, that could destabilize the helicopter. Vortex ring state was a major problem in V-22 Osprey. So because V-22 Osprey, I don't know if you have seen this, it's a tilt rotor aircraft. It would actually take off as a helicopter, and in mid-flight, the rotors would rotate, and then it would fly like a plane. So it can hover in place, but also it would be as efficient as the fixed wing state. Initial V-22 accidents happen because of the vortex ring state. Because in the helicopter mode, or when it transitioned from the flight mode, it came down so quickly. It lost the altitude so quickly that basically that destabilized the aircraft. In my personal experience, if you look at the quadcopters, I do not know if that problem is as severe because I have not seen a very commercial quadcopter that is used to carry payload or humans. I mean, vortex ring state, that can happen in the case of helicopters. But when we are talking about small drones, usually I haven't seen the vortex ring state instability. If the quadcopter has to fail, it actually fails before the vortex ring state, that state appears. That's just my personal experience, but that was very common. So what they did is V-22, and I know this because they implemented that in Bell 609. So basically, there was a system override. If the pilot wants to drop the altitude very quickly, the system would prevent it from dropping the altitude. How would you drop the altitude? You would drop the altitude in the helicopter state by controlling or changing the speed. If the system sees there is something called as air data attitude heading reference system. So this is like a barometer, IMU, all that stuff. So basically it says that if delta H is very quick, then it will control the rotor speeds so that the vortex ring state will be avoided. But Bell 609 is a variant of Osprey. So they learned the issues and from testing, and they improved that. But you should take, if you have YouTube videos on vortex ring state, it's an interesting phenomenon. And that was major cause of initial V-22's accidents. Okay, so we are going to look at these individual blocks. So we are going to look at the thrust. Then we are, from that thrust calculation, we are going to find out what is the prop size that we need. Then from that prop size, we are going to find out what is the motor size that we need. From that motor size, we are going to look at what type of AC we need. And at the end, we will decide what battery we need. And once we have specified all these, then we will find out how long that system can hover, how fast that system can travel, or what are the performance specs or flight parameters that we can achieve with that particular system. And when I talk about these models are nothing but just equations. Most of these equations are nonlinear, and many a times what you need to do is you have to solve these equations simultaneously. So sometimes you have to look at the tables, you have to look at some numerical solution, or you have to go back and forth, trial and error. But at the end, once we have gone through this process, every single block has about 2 or 3 equations, nonlinear equations associated with it. And if you were to do a pen and paper calculation, you would step by step actually go and solve those equations and find out the parameters. And then if you notice that some parameters don't satisfy the design criteria, you have to go back and perform 1 or 2 iterations. So this is what I was talking about. This is called as the blade element theory. The blade element theory in the case of rotorcraft and in the case of fixed wing is slightly different, because if you visualize a rotorcraft, a quadcopter or a helicopter, what you have is you have this blade that is slicing the air. So as you can see, but nevertheless, what you have is you have an airfoil. So you can see that airfoil is at angle alpha, and then there are going to be 2 components to it. There will be a component of force perpendicular to the airfoil, which is actually the lift, and there will be a component which would be parallel to the airfoil, that is drag. So DL is the drag, is the lift, which is given by 1/2 multiplied by CL. CL stands for coefficient of lift. This coefficient of lift is function of angle of attack. And if you have some exposure to aerodynamics, probably you already know, but if you do not have any exposure to aerodynamics, I want you to visualize this very simple experiment. Don't do this, just visualize. You are driving, put your hand outside, then you have make it flat. As you increase this angle, you would notice that you are going to get more and more lift. And after some time, if this angle is very high, you are going to just get drag. There will be no lift. So that's exactly what is happening. So as angle of attack is changing, the coefficient of lift changes. And what is the rho multiplied by W naught square? W is the incoming air velocity. 1/2 rho V square or 1/2 rho W naught square is called as the dynamic pressure. Dynamic pressure is, last time I talked to you about that if you look at air or a fluid, fluid has kinetic energy and fluid has pressure energy. When that moving air sort of comes in contact with this stationary airfoil, it loses its kinetic energy by converting that kinetic energy into pressure energy. And that pressure is called as the dynamic pressure. It's not a static pressure. It's called as dynamic pressure because, think about it, this moving air comes in contact with this fixed or stationary surface, stationary relative to the moving air, stationary relative to moving air. This surface could be moving, but this is stationary relative to the incoming air. So what happens? This differential velocity or differential kinetic energy gets converted to pressure. If you don't believe me, remember the drag experiment I talked about? Just put your hand outside and you will realize that you are being pushed. Why are you being pushed? Because the incoming air, when it comes in contact with your palm, it is going to lose certain amount of its kinetic energy. That kinetic energy gets converted to pressure energy, and that actually pushes your hand back. So what you have is, you have the dynamic pressure multiplied by C times dr, which is nothing but the chord length multiplied by the radius. Now, what is chord? Chord is this distance. This is the chord. Chord length multiplied by radius. If you integrate the left hand side and if you integrate the right hand side, you're gonna get the complete expression for the lift. Same thing happens with the drag. The only thing is the dynamic pressure 1/2 rho v square or 1/2 rho w naught square gets multiplied with CD. Now, what do we desire? We want low CD, we want high CL. But unfortunately, it doesn't happen that way. So depending upon the different types of airfoils, you have certain CD and CL characteristics. So that's why you have to kind of choose what air do I use, NACA type of airfoil, NACA 1025, or what type of airfoil I use and what type of CD characteristics that I need. Now, if you look at the pitch angle, so basically what's going to happen is there will be some angle of attack, but the aircraft is going to pitch. So what it means is the total angle is going to be the angle of attack alpha plus theta p, which is the pitch angle. And then once you equate, what happens is usually, even though I said that the lift is sort of perpendicular and drag is sort of parallel, because of the shape of the airfoil, it's never perpendicular and parallel because it's not a flat plate. It's never going to be perpendicular and parallel. There will be some angle gamma, and that gamma angle is shown over there, and that is nothing but the tan inverse of drag force divided by lift force. If you were to find out the resultant of lift and drag, that is given by dr. So dr is the total force, which is the resultant of the lift force and the drag force. And at the end, if you want to find out what is the total thrust, this is very important. Total thrust is the component of the resultant force in the vertical direction and the component of resultant force. Resultant force is dr. The cosine of theta naught plus gamma is going to be dt. Remember this equation? dt is the thrust that we are looking at. Everyone understood this? So this is the basic blade element theory that you should understand. And depending upon what your interests are, you are welcome to take rotor dynamics course, rotorcraft course, and they will talk about these equations in lot more detail. So here is the basic idea. How do I find out the lift? To find out lift, the simple equation is dynamic pressure multiplied by the coefficient of lift multiplied by the area. Pressure multiplied by area gives me force. That multiplied by the coefficient of lift or drag is going to be the lift or drag. So CL multiplied by the force gives me lift. A CD multiplied by the force gives me the drag. So what I'm doing here is I'm substituting the values of blade area. So I want you to look at this equation, which is lift is equal to CL 1/2 rho V square dynamic pressure multiplied by blade area. That blade area is actually, since there's something important. There is a disc, so as this is rotating, this is like a disc, but this is not a full disc. This is like a partial disc. So if I want to find out the area, what I have is I have something like dp cp multiplied by lambda multiplied by bp by 2. Bp is nothing but the number of blades. So basically, what I'm going to do is I'm going to find out an area, approximate area for that blade. And that lambda factor is because I don't have a full circular blade. I just have a part of the blade that is kind of rotating. So that is the assumption for the area multiplied by, I have the speed, where again dp n by 60 gamma pi, that gives me the angular velocity, and that is squared. So once you expand that equation, what you do is you actually do a little bit of mathematical jugglery and call something called as aspect ratio. So aspect ratio is a dimensionless quantity that is used to characterize different type of airfoils. And the reason is, if you were to look at the aspect ratio, it's a non-dimensional quantity that can be used to compare different shapes and different size. And then at the end, I want you just to look at equation P. Equation P is the thrust is given as lift divided by cosine gamma minus delta, which is the downwash correction angle, is because even though we expect the velocity to be, or the air velocity to be going like straight down, it never goes straight. Basically, there is a diffusion and there is something called as the downwash. The rotor is pushing the air down. So basically, you get some correction to the gamma value, and that is the downwash correction angle. What that means is torque. Thrust. P. This is the most important equation. P is equal to Cp, which is the thrust coefficient multiplied by rho multiplied by n by 60 d square, n by 60 square multiplied by the diameter to the power 4. So what that means is the thrust given by a prop is dependent on the diameter of the prop and the speed of the prop. Diameter of the prop we cannot change in runtime. So the only thing that we are going to change to adjust the thrust is speed. Everyone understood this? This is the most important equation. Now torque. So once you look at the equation for torque, please understand the thrust equation has its roots in a coefficient of lift, CL. Can you see CL is popping in there? The torque is dependent on CD. So basically, you would have the same thing. CD multiplied by 1/2 rho V square multiplied by the projected area, and then you get and please note, torque means you have the force multiplied by the radius. So that's why that gets multiplied with one more D. And then if you formulate this equation, let me move this a little bit here. Okay. Now, if you look at this equation, you would notice that again, you have the number of blades, coefficient of drag, rho, and then again, you have the projected area, and then you have one more D because that is force multiplied by the radius. That is the reason why this is super important. The moment equation or the torque equation is proportional to coefficient of moment or Cm multiplied by rho multiplied by n square by 60, but the diameter of prop to the power 5. Why? Because it's a torque, it's a moment. So you have force multiplied by distance. That's why you have that equation. Again, there is a linear analysis and nonlinear analysis, but as soon as when you go into the nonlinear analysis, the equations become super complex because aerodynamics is not straightforward as we talked about. But as far as we are concerned, our quadcopter modeling is concerned, our equations are concerned, these are the two most important equations that you should keep in mind. And as a matter of fact, these equations are implemented in okay. So now we just talked about this thrust model. Now in thrust model, the most important thing here is the speed. But please understand, air density is also a function of temperature. Air density is also a function of altitude. So there could be some correction to the air density depending upon what is the pressure. And as you know, that as we close to the Earth's surface, air is more dense. As you go up, air is gonna become less dense. And then again, it also depends upon the temperature. So there is some relationship between the density and the reference density, which is the density at standard STP. And then But for practical purposes, you can just use the value of rho as 1.2 and you should be okay. Then there is something called as this inverse thrust model. So how would you start the design process for a multi-rotor? First and foremost, you want to make sure that that multi-rotor is able to lift itself. So what you do is, first you'll find out the amount of payload, and then you'll find out the approximate self-weight, and then you'll find out a particular prop, and then you'll find out the speed at which that prop has to rotate so that you basically, that quadcopter or an octocopter has enough thrust to lift itself, the payload. And then what you do is, you actually look at the G, which is the weight, and then you can use the equation for the thrust, and then you actually find out the value of speed. And this speed will tell you that what would be the motors to choose, what would be the EACs to use, what should be the kV value of the motor, and what should be the EAC that is going to supply the current to that motor to support that kV value, and then you will find out the battery. So then once you've done with thrust, then you will find out what is the torque. So you have to use this moment equation. So you will have this Cm, which is called as the torque coefficient, and from the torque coefficient you are going to find out so torque multiplied by speed is going to give you the power. So basically that will identify what would be the power that needs to be supplied by the motor. And then how would you look at the motor model? So motor, very simply, will be given by the torque given by a motor, which is Te, is equal to the torque coefficient Kt multiplied by the current that is supplied to the motor. And then again, there is some scaling factor that you can use. And typically, I don't know if you have just seen this equation. I want you to think about this equation for a second. Kt is the scaling factor, Kt and Ke. So it's a 60 divided by 2 pi. But if you think about Ke multiplied by Kv multiplied by UMO, which is the voltage supplied by motor, which would be the no load voltage UMO minus the current that is flowing through the motor coil multiplied by the resistance of the motor. So the bottom equation, what you see is nothing but the back EMF equation for the motor. The bottom equation, Ke is equal to U0 minus Im0 Rm divided by KVO multiplied by UMO is the equation for the back EMF of the motor. And usually these parameters are provided by the manufacturers. So how would a brushless DC motor look like? So basically, as you can see, a brushless DC motor is like a three-phase motor. Think about it like you have switches. So switch 1, switch 2, switch 3. And what you do is, basically you sequentially operate those switches so that the DC current that is going through gets sort of switched. And then instead of a straight constant current, you are going to get some sort of sinusoidal current. And this switching happens very, very fast. So that's why you get a three-phase out from a single DC input. This is the equivalent motor model. So what you have is, you have UM, which is the voltage. You have Rm, which is the resistance of the motor. Which you have Lm, which is the inductance of the motor. And then the back EMF equation that we just talked about is derived from this equivalent motor model. And so the output torque, which is the torque at the prop, is Kt, in the parentheses, the differential current, which is the current flowing through the motor armature or motor coil minus the no load current, and that gives you the torque. And with these equations, what you can do is you can find out the equivalent motor current, and then you can find out the equivalent motor voltage. So these two equations are applicable when you are trying to identify what motor to choose. So first, start with the thrust, decide the prop, find out what is the speed the prop has to rotate. From that speed, select the appropriate motor. From that motor, you make sure that the thrust is what you need, the torque is what you need, and then go on to the next step, which is the design of ESCs. So ESC is a very simple circuit approximation. So what we are going to assume is you have a incoming voltage, then you have the resistance, and you have the current that is flowing through. Then now one thing I want to tell you, which is if you have not seen how the ESC looks like, please notice that ESCs on the input side has the battery terminals, and it has this PWM. The speed of the motor is proportional to the PWM signal that is supplied to the ESC. So that sigma is nothing but the PWM command that is supplied to the ESC. So sigma of 1, which means the full voltage is supplied and the motor is running at its full speed, full rated speed. If sigma is equal to 0, which means the motor is not rotating. So sigma is sort of called as the throttle. So 100% throttle to 0% throttle. And that is how actually you can approximate that something like, just to give you a simple example, if you look at the brush DC motor, if you apply 1 volt to the brush DC motor, it will rotate slowly. If you apply 12 volts to the brush DC motor, it will rotate fast. So fully supplied, actually fully rated voltage to the partial fraction of the voltage will dictate how slowly or quickly that motor is rotated. So that you can think about like a throttle. And then ESC command can be related to the current that is inputted to ESC, because please try to understand that ESC is not going to supply motor the voltage that is more than the voltage supplied by the battery. So whatever current capacity, whatever voltage capacity the battery has, that gets supplied to the motor through ESC. So that is when the battery resistance come in the picture. As you can see, there is UB, that is the voltage that is supplied by the battery, minus the number of ESCs, because ESC, they have their own wiring, their own circuit. So there is some resistance to it, multiplied by the current that is flowing to the ESCs. And then what you do is, if you want to decide the battery capacity, once you have identified the number of ESCs, what are the properties of the ESCs, what you can do is, you have to take into account the other things that you are running, like autopilot, LEDs, grabber, gripper, some sort of GPS receiver, and so on. And then all that load gets added when you decide the battery. So for battery, what you do is, you want to find out the minimum battery capacity. Battery capacity is usually given in milliamp hours. So amp hours is, it's like 30 amp hours, which means the battery would be able to supply 30 amps for 1 hour. So depending upon that, you can actually decide the type of battery. And again, battery, they're depending upon the chemistry, size, weight, power density, they change. So in short, we talked about all these equations. These equations, when you combine, they give you these nonlinear equations. Sometimes you can solve those sequentially, but many a times what you have to do is you have to go back and forth, because you would go through the design process and you realize, hey, uh, I, I don't have this ESC available in the market, but I have something else. So what do? Go back, change the product, do some type of iteration, and then follow through this cycle. So these equations uh, can be used to solve 4 typical problems. So how would you design a UAV? And I will walk you through actual design exercise, not now, later. But the first thing what you would do is you will try to make sure that the UAV is able to hover. That is the first and foremost thing. And to make sure that the hovering is possible, hovering is stable altitude hold. It's never done at 100% throttle. You do not want 100% throttle, and what UAV is doing is just hovering. You want it to go from one place, point A to point B. Usually, the stable hover is done at 50%. So what you do is you choose 50% throttle and then work out these equations and then find out the capacity, whatever components that you need. The next part that you look at is then you see what is the maximum thrust that UAV or that system is capable of giving out. So once you have your basic parameters decided, you want to find out what is the maximum thrust that can be generated. So what you do is you change the throttle value from 50% to 100% and then find out what is the thrust that is generated. And next problem what you see is then you observe is that propulsion system is able to give me a stable forward flight. So which means, am I able to take that UAV from point A to point B, either in X plane or in Y plane? So that is the third problem in the design problem that you want to solve. And then here, that kind of actually tells you that how much of payload can be carried out and how long that payload can be carried out. So whether it can be carried out till 10 meters, 15 meters, 50 meters, 100 meters, and so on. And the last problem is you want to go from point A to point B at the maximum speed. So for that, what you do is you basically use the exact same equations, but in that case, you add certain pitch angle, because as you know that the quadcopters are under actuated systems. So you have to have certain pitch angle, but please understand, you cannot pitch quadcopters beyond certain pitch angle because they would actually flip over. They are not inherently stable. So you would have a design pitch angle, and then you will find out in forward flight mode how far it can go, what is going to be the relationship between the thrust and drag, and then what would be the realistic forward flight speed that UAV can achieve. And then clearly with that, you can find out the maximum flight distance. And usually there are some constraints, and these constraints we need to take into account in the design stage. And the software that we use for designing usually would have these constraints implemented, because you don't want battery to discharge than its capacity. So if you have C15, you don't want to discharge it more than C15. And many a times at initial level, this is the jig that they use. So you actually have a motor, you have a prop, you have an electronic scale, and basically you run the motor at different speeds, find out the value of thrust, and then basically characterize the speed and the thrust characteristics of the motor. And then you have experimental results, and then you compare that with the theoretical results, and then see how close they match. So what I want to do is, I want you to go to this website, which is called flyeval.com. Online students, I'm going to change my screen. So So I want you to go to flyeval.com. So I just want to make sure that online students can see this flight evaluation GUI. So here, what you can do is you can actually specify the type of helicopter, type of multi-copter you want. For example, this is an 450 frame. So you can see the frame size is 450. At what altitude you want this rotorcraft to go? So I said 20. What would be the air temperature? What would be the design? You want that design to be excellent, most efficient, poor, very poor. Then what is the battery capacity? What is the takeoff throttle? So you can say 75. Then flight control unit, tilt limit. So you can add certain tilt limit on this, or you can actually just leave it no limit. Then you can select certain brand of the motor. So depending upon what motor you choose, can you see that it selected a particular motor? Then you can see the particular prop that you choose. Then what it will do is for that prop size, for that prop brand, for that motor, it will actually pick up the prop. Then you have to select the proper ESC size. So you can see that 40 amp ESC. Then you can actually do the battery, and then you can actually do the calculation, and then it will actually do the design calculations. Many a times it will tell you that these specifications, what you're trying to achieve, is outside the scope of available components. So one easiest thing to do is there are some standard frames. For an example, a tricopter, this is a standard frame. Run, it will run through these calculations, and you will just, I'll show you what it will do. So run through the calculations, and basically it will give you all the 4 design problems that we just solved or we just talked about. Like it will give you the hovering time, it will give you the load carrying capacity, it will give you the takeoff altitude, it will give you how far it can fly, it will also tell you how fast it can fly. Everyone understood this? So the advantage of this tool is that it actually talks to the database and then picks up and applies the constraints that we talked about. If you go down, you can actually go, it will give you a lot more details on the performance characteristics of ESCs. If you go down further, depending upon the frame that you have chosen, it will actually tell you what is the mass, what is the inertia matrix, what is the diagonal matrix of inertia, and all that stuff. And all these properties will be very useful when we actually do the dynamic model of the quadcopter. From next class, we are going to look at the dynamics of quadcopter and simulation. So some of these parameters would come in the picture. And then if you want to see the equations, how these equations are implemented, you can just click on modeling method and source code, and it will tell you the equations, how the equations that we talked about are implemented in this GUI. These are the exact same equations that we talked about. Prop design, the equations for prop, equations for motor, equations for ESC, equations of battery. And in next class, we will try to do this with MATLAB. But I would strongly encourage you to take a look at modeling methods and source code. Just click on that. The next iteration is, I want you to look at the design. So this is like design of experiment. What if you were to change certain parameters, or what if you play with certain parameters? So for an example, if you choose the quadcopter, and then if you want to select the database, which is the T motor, and if you reverse solution, then it will tell you what are the possible options. And if you were to swap some of these components, what would it look like? So what would it do? So if you are interested in performing some sort of design of experiments, or for example, if you don't have certain motor in stock, but you have something else in stock, then you can actually do this and see how well it will perform. So I would encourage you to just take a look at this code, and this is very well done. Any questions? Yeah.
We need quadcopter also, the UAV to carry a payload. Do we take into consideration
We add the total load. Yeah, total weight. The quadcopter weight will get added to the payload.
What if my weight is variable? It depends on the object that I'm trying to grab.
So you will design your quadcopter to the maximum, the heaviest possible object that your quadcopter is going to. The problem is not that simple. I'll tell you the problem. There is an issue from something called as the sling load. For an example, if you have a load that is rigidly attached to the quadcopter frame, lifting that is easy. But if you have a load that is suspended from the quadcopter, lifting that is going to give you the load and the moment. So the regular helicopter pilots, for example, the helicopter pilots that you see, they carry patients from one hospital to other hospital. They are not certified, typically not certified to carry sling loads. The rescue pilots, like people who basically the helicopters that rescue people, wherein you have the rope, or the helicopters that are used for fast roping or dropping people, they are certified for sling loads, because sling load gives additional mode of instability in the helicopter. So it totally depends upon what type of load you are carrying. Perhaps if you have a rigid grabber, and if you grab and rigidly grab, then your load, the load capacity what you need is different than if you have a grabber that is swinging. Because then basically you have this coupled dynamics that actually destabilizes the quadcopter. So if you get a chance, if you go on to my YouTube videos, we designed a quadcopter gripper wherein the dynamics of the gripper was decoupled from the dynamics of the quadcopter. So you would see that there's a quadcopter, there's a counterweight, it is grabbing that microplate, but you will notice that the instability actually counterbalances that microplate, but the quadcopter is stable. So basically it is decoupled. So there are techniques to decouple the sling load from the quadcopter.
Decoupled system, you mean that the dynamics of the quad.
Dynamics of the dynamics of the grabber is not affecting the dynamics of the quad.
Okay, the UAV will act accordingly.
UAV will go its way whether even though there is load or there is no load. It's something like a counterbalance. Okay. Any questions from my online students? If there are no questions from my online students, this would be a good time to show you the Parrot Mambo programming. So if you have Parrot Mambo, please take it out. No, we are not going to use the equations by heart. We are going to use MATLAB and Flyval to solve the equations. Okay. Now I'm trying to find out what is the best way to do this. Okay, I want you, can you see my screen? In your screen, Go to add-ons. Everyone, go to add-ons. Manage add-ons. Everyone has Mambo, or most of you. Mambo. USB cable, micro USB cable. Attach micro USB cable to Mambo. Micro USB cable to Mambo. Yeah, your Mambo should be propless. I'm just gonna show you prop, but I'm gonna run those at 10%. So okay. Next, as soon as you hook it up, you will see that Mambo comes up. ELF is the firmware, by the way, Mambo's firmware. Then you should go to Simulink support package for Parrot mini drones. Online students, can you see my screen? I don't know if you can see, I connected my Parrot Mambo drone to USB. Go to setup. Then it will give you a prompt. Next. It should automatically detect Parrot Mambo. Everyone here? Yeah. First, your Windows to detect Parrot.
Yeah.
You got it working, right?
Yeah, I got that.
Don't have Parrot?
Our only cable.
Everyone here? No, no. Please. Huh? You need battery. I haven't attached my battery. And I have 1, 2, 3, 1. So what I'm gonna do is I'm gonna show you what happens. Then I will loan out these batteries. But please return these batteries before you go. So next, everyone here. Next. Now it's gonna flash the firmware. How do you know that firmware is flashed? Eyes will blink. And then they will turn green. Now at that point, there is the connectivity light that should be blinking. So that means the firmware is updated, but now it needs to do its own reset. So take this battery, put it inside. Okay, and now watch. Oh, I put a dead battery. Yeah. So yeah. Basically, so show everyone. That is means the firmware is getting updated. Yeah. So your firmware should get updated. So it will actually sequentially go. Yeah, that means the firmware is updated. It's still going, right? So that means the firmware is getting updated. It will get hot. So firmware. So this is what should happen. Plug the battery. Pull it out. Then basically it should restart. It should, and then it will actually. Yeah. So this is what will happen. And then finally, it should go back to a stable link. Yeah, that is how it should be. It should continuously blink. That means the firmware is successfully updated. If the firmware is not successfully updated, it will give you some sort of warning. Next, this is an important step. You need to connect Parrot drone to USB. Parrot drone to USB. Go to device drivers. Go to device managers. And then you need to go to RDNIS. So you should see, you would actually see a new device which is RDNIS, remote NDIS. And then you should update the driver. No, it should not automatically, basically Microsoft. Yeah. Then let me pick up. Then go to network devices. Go to Microsoft. Go to Microsoft. No. And then choose the Microsoft DC remote NDIS. Remote, yeah. Remote. Go down, this one more. Yeah, remote NDIS compatible to that. Yeah. Here. Yeah. What? Yeah. Yeah, coming. Try this. No, it will work. You have it? Okay, I'm gonna stop here. The instructions for updating the firmware are online on Macworth website.